This lecture and example will illustrate the methodology required to make a hypothesis test about a population mean mu. So if someone makes a claim that is purported to be true about a population mean, we can use the methods of general hypothesis testing that were covered previously in a previous lecture in order to determine whether the claim is true or not. Whether we find evidence to support or not support the claim, or reject or not reject the claim, can be found. And when we test claims about a population mean, the rule is basically identical to that we found when we did confidence intervals. So when we did confidence interval estimates for a population mean, when we knew the standard deviation of the population, we ended up using z-score as our value in our error estimate. And when we did not know the standard deviation of the population, we ended up using t-score in our error estimate calculation. So when we do an hypothesis test about a population mean, the same rules apply. If we know the standard deviation of the population, we end up using z-score as our test statistic, where you would take the mean of the sample minus the population claimed mean, but use the standard deviation of the population over square root of n. That comes from the central limit theorem. When we have the mean of the population is unknown, we were forced to use t-score. So that other distribution, which is close to the z distribution, but gives you a correction for small sample sizes or cases where the standard deviation of the population is not known. Because we don't have the standard deviation of the population, we end up using S, the standard deviation of the sample. So you take the mean of the sample minus the mean of the population over the standard deviation of the standard deviation of the sample over root n from the central limit theorem. So in summary, when we're testing claims about a population mean, if you know the standard deviation of the population, you use the z-score test statistic. So we take the mean of the sample minus the claimed mean of the population, and we use standard deviation of population over square root of n. If the standard deviation of the population is unknown, then in that case, we use t-score. Same calculation, mean of the sample minus the mean of the population, but you divide by the standard deviation of the sample divided by the square root of the sample size. So we have those two characteristics, those two test statistics that are used for all claims about population means. So here is a typical example. According to Health Canada, there is a limit to how much ionizing radiation a television may emit. Now, this used to be a significant issue when televisions were primarily cathode ray televisions, where a beam of electrons would be emitted, and then when it crashed into a screen, those electrons would decelerate and cause luminescence on a screen. The act of a decelerating charge would produce X-rays. And X-rays are an example of an ionizing radiation. And ionizing radiation is the type of radiation that is going to cause damage to human tissues. So it makes sense that the Canadian government would set a limit to the maximum amount of radiation a television can emit. The emission limit was a maximum of 0.50 milliröntgens per hour. Röntgen is just a unit that describes radiation, measurement of amount of radiation. Milli is the standard SI prefix, 10 to the minus 3. And it has to be 10 to the 0.50 times 10 to the minus 3 Röntgens per hour. That is the maximum amount. So a television manufacturer claims that their product performs better than this standard. So this is the standard that is being claimed, 0.50 milliröntgens per hour, but the company claims that their product performs better than this standard. So that means less than this radiation limit. In order to test this claim, a sample of 35 random televisions from their production run found that there was a mean exposure, mean radiation from their televisions of 0.57 milliröntgens per hour. So that is our sample that was used. Sample of size 35 yielded a mean value of 0.47. Now 0.47 is definitely less than 0.5. The question is it significantly less? Is it significantly less, statistically significantly less, that would allow us to agree with this claim or support this claim? We have additional information here that a previous study of all produced TVs gave a population standard deviation of 0.1 milliröntgens per hour. So because, and that's the dead giveaway right there, because the population standard deviation has been given, it means that we're going to use Z-score as our test statistic. So back to this, because the standard deviation of the population is known, we're going to use Z-score as our test statistic. So we need to go through the problem-solving steps in hypothesis testing. This was covered in a previous lecture. The first step is to write the claim. And so the claim that's being made is that their product performs better than the standard of 0.5 milliröntgens per hour. So if we write that in mathematical language, it means that the claimed mean, mu, is going to be less than 0.5 milliröntgens per hour. What we need to do is we need to take this and convert it to the null hypothesis and alternative hypothesis. So, because this claim is mu is less than 0.5 milliröntgens per hour, you'll notice that that claim does not contain an equal sign. Because it does not contain an equal sign, it must be the alternative hypothesis. So mu less than 0.5 milliröntgens per hour, that's the original claim. We are forced to make that the alternative hypothesis, H1, because it doesn't contain an equality sign. The opposite of that claim must therefore be the null hypothesis. The only thing that allows us to be not less than 0.5 milliröntgens per hour would be, the opposite of that would be greater than or equal to. So notice there is now a equal sign inside of that null hypothesis. So in order to do every hypothesis test, what we have to do is we have to operate with the significance level that we are given. And in this question, we were told to test the claim to a 5% level of significance. So that means alpha is 0.05. The level of significance is the percentage of experiments of sample size 35, that if we repeat the experiment, it's the percentage of these that we are allowing to disagree or disagree with the null hypothesis just by random chance. And so that's not a particularly high level of significance, but it is one of the more common significance levels. So we need to build or draw this claim. So we know that the emission limit is 0.5 milliröntgens per hour. So if I sketch a normal distribution of sample means, a normal distribution of sample means is going to have mu of 0.5 milliröntgens per hour. That's the claimed mean on the equal sign for the null hypothesis. That's going to be in the center of the distribution. According to the null hypothesis, anything that is bigger than 0.5 milliröntgens per hour will actually agree with this hypothesis. So if any sample mean gives us a value which is bigger than 0.5 milliröntgens per hour, that's going to be fine. What we need to find is the rejectable region, the region that disagrees with the null hypothesis. Remember, you only ever sketch and only ever test the null hypothesis regardless of whether it is the original claim or not. So, if greater than or equal to 0.5 milliröntgens per hour is fine, the only place on this distribution that will allow us to find a sample that will reject this claim of the null hypothesis is if we find a value that is significantly less than 0.5 milliröntgens per hour. So that's only on the left side. So this is why this is called a left tail test. It is only on the left side of the distribution. We can find, if we find a sample then that is in that critical region, so significantly less than 0.5 milliröntgens per hour, it will allow us to reject the null hypothesis. We can find the value of the test statistic from this sketch. So from this sketch, we can look on our table of z-score values. And we are looking for a 0.05 area that is to the left of that z-score. So a 0.05 area, if we look on our z-score table, 0.05 looks to be 0.05 right here. 0.0505 and 0.0495 are the two closest values on our table. The area of 0.05 falls right in the center of those two. And so if we read the table, that's a z-score of negative 1.64 or 1.65. If I go halfway between the two, I get a critical score that separates the rejectable region from the acceptable region of negative 1.645. So from our table, we find a critical z-score of negative 1.645. In order to complete the hypothesis test, all we have to do is calculate the z-score that corresponds to this measured average of 0.47. We have to use the z-score test statistic. So if we use mean of z equals mean of sample minus mean of population over standard deviation over root n, we just plug in our numbers. The mean that was measured for the sample is 0.47. The mean that was claimed for the population was 0.5 in the null hypothesis. The standard deviation of the population was given as 0.1, all in milliröntgens per hour. So those units are all going to cancel and we get a unitless measure. We divide by the standard deviation of the population, 35, square root of 35. And so if we take 0.47 minus 0.5 and divide by 0.1, but multiply by square root of 35, dividing by the square root of a number on the bottom of a fraction is the same as multiplying by that square root on top. If we multiply that out, we get a z-score of negative 1.77. So our sample yields a test statistic of negative 1.77. Negative 1.77 is, for our sample, left of the critical z-score of negative 1.645. So our sample average of 0.47 milliröntgens per hour does lie in the critical region. It is significantly less than the claim of 0.5 milliröntgens per hour. So now we have to make a conclusion. Since our sample lies in the critical region, it means that we have to reject the null hypothesis. So that z-score is in the critical region. It means we reject the null hypothesis. If we reject the null hypothesis, then that means that we're saying claim H0, we have evidence to reject it. But remember that the conclusion of the hypothesis test is always related to the original claim, whichever it may be, null or alternative. So if the original claim was the null, we would have evidence to reject it. But since it is the original claim is the alternative hypothesis, if I have evidence to reject this claim, it means I have evidence to support this claim. And so your conclusion should say that there is sufficient evidence to support the original claim that mu is less than 0.5 milliröntgens per hour to a 5% level of significance. So we have found from the sample data, since the sample average 0.47 was less than the claimed or tested number of 0.5 milliröntgens per hour, and significantly so, to a 5% level of significance, it means that we would reject the null hypothesis and therefore support the alternative. But that is only true to a 5% significance level. What if we had a different significance level? Maybe, if we had a 1% significance level, that would mean our area to the left in this left tail test would be 0.01 instead of 0.05. And if we look on our z-score table, an area of 0.01 is right here. It's going to be between negative 2.32 and negative 2.33. It looks closer to 2.33. 0.01 closest on our z-score table is 0.0099. So that would mean our critical z-score would be negative 2.33, not negative 1.645, which means our sample test statistic would not be in the critical region anymore. Negative 1.77 is not less than negative 2.33. So we, at a 1% significance level, would not find sufficient evidence to reject the null hypothesis. It means we found a value that was less than the claimed average, but it wasn't significantly less, so we wouldn't be able to reject this, which means we wouldn't have evidence to support this. So remember, that's not a very strong statement. It's saying you would say, we had insufficient evidence to support this claim. It doesn't mean that claim is false. It just means you didn't find statistically significant evidence to support the claim. In order to support the claim, you would probably therefore have to drive up the sample size. Because as you drive up the sample size, it's going to make your test statistic, if this number goes up in the denominator of the denominator, it's going to increase this value and drive your test statistic more to the left and put it more likely into the critical region. Anyway, in summary, in this question, the original claim was the alternative hypothesis. You only test the null hypothesis, and we found that our test statistic was in the critical region, which allowed rejection of the null hypothesis. If we reject the null, it means we must support the alternative. And so that is the conclusion of this hypothesis test.